now to introduce our next speakers, multiple speakers. So one of the advantages of going to a virtual meeting actually has been that we're able to reach to our speakers in a different way. And I think ZH Code, Zaha Hadid Architects were the first to adapt to the new environment. When I was talking with Shajay about the presentation, he said, well, can I bring other team members in? And of course, that would have not been possible on the physical one with the setup that we had. So they are going to be presenting as a team. And I think that's a perfect reflection of how we do work. We work as a team. And when we have these conferences, we kind of spotlight one person in the team. We know we can't make it on our own. So it's a perfect example of how we work. We invited ZH Code because they are at the forefront of computational design. For those of you who are not familiar with what computational design means, you will become familiar after this talk. Brad, in his presentation yesterday, touched on it as one of the drivers for the future, and how are we going to integrate that into our design process? How are we going to change how we make things, not just think about things? And how do we make it relevant to what we do? So I am very honored that they accepted our invitation and have taken it very seriously to explain what they do. I would like to welcome, I think Shajay is starting off. Yes, welcome ZHA Code, Shajay Bhooshan, Vishu Bhooshan, and Henry Louth to this virtual stage. You can share the stage as you wish now. Just have to press share screen, I think.
Thanks a lot, Salma, for the introduction and also the invitation to speak at the conference and kind of illustrate or outline like the various efforts that that are underway in the field of like computational design, and how digital transformation in architecture is actually significantly underway, and it's a exciting domain and also exciting opportunity for architecture to kind of reclaim its position as one of the leading technologically advanced professions. And originally, like when the conference was meant to be physical, we were excited to know that or discover that Sarasota has a kind of deep history in supporting experimentation, like somewhat similar to the Bauhaus in Europe, and the Bauhaus has been a very instrumental reference for us at Zaha Hadid Architects, as you will see across the three presentations that we will make today. And you might see how through our research collaborations, particularly with the Block Research Group at the Institute of Technology for Architecture at the Swiss Federal Institute of Technology, we are trying to genuinely learn from like the previous centuries, try to upgrade some of the techniques and knowledge that is held in the built environment through the use of computation. So like the way we're going to do it is I will just generally provide a broad overview of how our research agenda and like our interest and motivation for the last 13 or so years at Zaha Hadid Architects. And then Henry and Vishu will take it further and provide you far greater detail about how we apply some of this research on projects, and also project-based anecdotal information and so on. And the two main topics that we will apply, or we are trying to apply our research in, our design of complex geometry buildings, unique cultural buildings, and so on. And the other bit is mass buildings, like particularly housing, and of and the common interest and thread that ties all of it together is so-called architectural geometry, and we will kind of, this presentation will kind of give you an overview of how that is related to Gaudi and Bauhaus and everything else. So I've been working at Zaha Hadid Architects for the last 13 years, doing my PhD at the Block Research Group. And also I've been teaching at the Design Research Lab at the Architectural Association in London. We at Zaha Hadid Architects recently completed this Beijing airport at the end of, already a year ago, at the end of 2019, and alongside, almost similarly, similar time, we had also completed this tower, which is which contains the world's largest atrium, which is a kind of homage to John Portman, and the kind of invention of this atrium like typology that he pioneered. And but what's interesting about these two buildings is technologically, the seeds were sown already a decade ago, like in 2010 or so, when a lot of the CAD, the investments in acquiring expertise in managing all this complexity, but also human talent, like, you know, we were people who joined from Gary Technologies into Zaha and so on, and particularly Cristiano Ceccato, who's been instrumental in the last decade of technological transformation at ZHA. So when we founded the Computational Design Research Group, which is the group that I lead, you know, the idea was to have our own version of that, like to build up research for the next decade and contribute to the next wave of projects, and which you will see that we are beginning to do. And so, like, how we can not only produce unique buildings, but like also transfer bidirectionally, like learn from the more mass building or the larger built environment. So in that sense, where I work, where I learn, and where I teach has been kind of instrumental in both of these, and in trying to make this happen. And what we mean by this is kind of correlate research with practice, and computation and technological aspects with design. And more graphically, what that means is, like, most of our time is kind of, or equal part of our time is spent on, like, kind of exploring these fun algorithmic inventions from the world of computer graphics, from the world of computational geometry, etc., and kind of trying to apply that to more architectural, let's say, problems like this facade design, which kind of tries to minimize, put panels only where there's high curvature. I mean, things are flat, like you use larger panels, for example. And so this kind of approach, like, helps us, like, also automate and control quality all the way downstream. So even though it starts with a very playful experiment with no less than maybe about 200 lines or 300 lines of code, and then, but it begins to yield results and fruit, like, all the way downstream, like it's trying to capture the constructional aspects ahead of time in the conception of shapes. So that's one idea of one of the applications of how computer graphics and so-called architectural geometry is intricately linked. And so too also with robotics, which is a new domain in the field of architecture, maybe 15 years of keen interest. Of trying to apply industrial robots from the automobile industry into the construction industry. And so again, we start with simple experiments like this $25 robot, trying to instruct that and subsequently scale it to a slightly bigger robot, and instead of start designing a proper pen holder, and subsequently, you know, like these things get more complex, and so allows us to kind of scale and to the point that we were then able to design for specifically robotic cutting. And so all the geometries that you see here were produced by the robots at the back, and like, so the shapes here, again, Henry and Vishu will articulate this in far greater detail. It's more that like there is a direct correlation between the capacities of the robot and this geometry. So these shapes are not willfully drawn, but they're drawn specifically to match the constraints of what the robot can do. And you will see also that this significantly helps reduce manufacturing time and saves material and so on. And likewise, we have also interest in topics such as curved origami, which is a kind of cousin, a curved cousin of straight line origami or straight line paper folding. And what's interesting about that is like you get curvature and variety almost naturally out of the process. And what is the process? You just cut paper and fold, and so you get this kind of and the other interesting thing about such topics is that there is a design method which is directly related to the method of making making the object. So here we draw in 2D the patterns in 2D. We discover fold lines and draw them, and subsequently only fold them into this 3D shape. So the entire shape is made of like one singular piece of plastic in this case. So there's no gluing, joining, or any. So this shape will unfold into this singular piece of paper. And what can be done in paper can also be scaled. This is also another key principle of all of these experiments, is that like similar to the robots, what you can do with a small robot, you can scale up. And similarly, what you can do with paper, you can scale to other sheet materials, which we did here. And anecdotally, what's interesting about this is that this was produced in India with hardly any digital economy at the time, like so. And was produced also in just a few hours by folding metal by using hands. And like we then subsequently try to capture this intuitive aspects digitally. So until then, like all the design process was a physical process, just fold paper, draw on paper, and fold, etc. And like somewhere alongside, we were also scaling, making very large scale installations like this one for the Venice Biennale, which was like not folded by hand, but folded by robots. But most of the intelligence was in the geometry. So the robots were themselves just automating some of the tasks. And we bring a similar kind of thinking when we are thinking about new technologies such as 3D printing. We are, in fact, like as part of my PhD, I'm trying to explore the relationship between unreinforced masonry and 3D printing in concrete. And this analogy goes just beyond the visual analogy. It goes far deeper, because masonry is compression dominant, meaning there is no steel or tensile capacities, and also it's orthotropic, meaning that you can shear away along these layers. And so printing and masonry share more material properties as well, not just, but most importantly, the design techniques that can be applied to masonry could potentially be adapted to the design of shapes that are possible using 3D printing. 3D printing in concrete in particular. In other words, we are seeing what can we do with bricks, and if you just scale them down, and we can do something similar with micro bricks, right? And also we are kind of trying to capture how to represent each of the layers, each of the bricks, or each of the brick courses, or each of the print layers digitally. And so for that we are borrowing MRI scanning technologies, or computational image technologies, rather than the more traditional, typical ways to represent geometry on a computer. So so each of these layers corresponds to each of the layers in the 3D printing. Each image corresponds to each layer on the right. And you can see why this is important to do in the early part of design, because these paths like have a direct imprint, like and a presence in the physical object. And this was a node that is all materially integrated. It's not 4 different parts coming together. It is printed in one go, and so it's materially kind of fused. And so that's also advantages. And so these seam lines are a integral part of the technology. And so we want to be able to give designers the opportunity to manipulate them. So in that sense, like the kind of cow that you saw, like which we were playing out with in the computer graphics world, is kind of really we can call it kind of optimized. And what it's optimized for are 2 things. One is it's optimized for production, i.e. like structural performance or constructional logistics or fabrication aspects. But more importantly, it also allows designers or frees up designers to be able to focus on storytelling aspects, which is a critical part of architecture. And again, this is not particularly new or unique to architecture, and this is another kind of synergy with the world of computer animation, computer graphics, and movie making. Whereas one half of the team on any movie, including the audience, is more engaged on the left side of this image. What are the characters doing? What are the expressions? What is the lighting? What is the storyline? So on and so on. Whereas behind the scenes, there is like several PhDs worth of technology on how to simulate the snow, how to simulate the fur, and even how to simulate lighting and so on. So this kind of synergy between storytelling and technology, whereas technology really takes a backseat, but is enabling the storytelling almost, is what we are kind of really after. And again, this is even in the built environment, this is not very new. Like people like Gaudi, because they inherited the right side of this image, like particularly geometry-based ways of calculating structural stability. So he was able to compute the stability of like these arches and stone blocks with very simple graphical methods, pre-computer time, obviously. So these triangles drawn here already kind of give insight into the structural behavior of these stone blocks. Sorry, 1 second. Yeah, so similarly, like all these geometrical knowledge and techniques was able to be transferred further into the building ecosystem through these manuals. So you didn't need to be an expert in mathematics or geometry to be able to draw the curves and draw the geometries such that they can be constructed. And these techniques are drawing techniques were also encoded or supplemented with these drawing instruments, which kind of were physical manifestations of the geometrical knowledge. um, so, so at this point, like I will take pause and launch the second poll, where I just want to highlight like what we mean by architectural geometry is geometry that is structurally informed and it's constructionally aware, and it is also environmentally suited, etc. And we will see that in the next section. And yeah, let me just launch the previous poll. Selma, I
Shajay,
think.
I did it for you.
Okay, but I think they already answered this one, right?
Uh, yeah, I can share the results of the previous one, or I think everybody just vote again now that you
Okay.
send it.
And also, like, if there are any questions, I mean, I'm happy to answer them now. If they're brief questions or anything that immediately pops in your minds, feel free to kind of send messages on the chat. Right. Okay. And so yeah, like so, what we are trying to do is kind of build up on the knowledge base that has been embedded in the built environment and in the techniques and also the instruments from a pre-computer time. And kind of upgrade it and make it adaptable to modern day technologies like 3D printing or robotic manufacturing on the construction side, but at the same time also on the design side, make it amenable or incorporate technologies from computer graphics, from the movie making industry, etc., into the design realm. And more specifically, what we mean by architectural geometry is that physical and machine parameters are abstracted as geometric properties. And maybe back to the origami example, what that means is that origami, in this case, you cut material and and also score the paper, and then you fold by hand, and you get curvature for free, and the shape is an automatic result of the physical action. So this is a physics phenomena, or a phenomena of physics, like where you're bending paper. But when you try to do that on the computer, rather than recreate the physics, what you try and do is to capture the geometrical properties, meaning when things are flat, um, like two conditions are true. Like in the flat plane, two conditions are true. All these squares and triangles will be flat, and also the angles along the angles at each of those so-called vertices, if you add them up, they will add up to 360 degrees because obviously in the flat plane they will be 360 degrees. So if you try and incorporate these two aspects, you will make sure that things are foldable. So the physics aspect is converted into two geometric properties, one of angles and the other of planarity. And we move the points until such conditions are true. And so you can see at the bottom that when the conditions are met, this particular shape is actually foldable. And so you can, so to make shapes foldable, the benefits of it for use of formwork and so on, you will see in Henry and Vishu's presentation. But in this case, we just made sculptures. Again, without needing anything more than a simple laser cutter, which was available in India, like because the person who had the laser cutting machine was using it to cut license plates. So we just made a deal with that, with that person. We exchanged some computational knowledge or which would make their life easier, and they cut this for cheaper price. But we were able to assemble these in a matter of a few hours in a relatively low-tech economy. So architectural geometry, in our opinion, is significantly better because it captures several of these physical parameters, like it's structurally, ecologically, and spatially better, and you will see how it's also helpful in preservation of building traditions, etc. So what we mean by better, it like offers better degrees of freedom for designers. For example, like in this tight space, we can create you know, far many user experiences than if we were restricted to you know, straight lines. And so, for example, we can create a somber mood on one side of this section and a more open mood and ambience and user experience on the other side. and um, and architecture geometry is also particularly ecologically better because in this example by the Block Research Group in Africa, they're able to span like large distances with the use of very weak material, like just raw earth bricks, which are sun-baked. And what that means is that you're inputting a whole lot less energy into the building, right? So you're not using the strength of the shape is not because of like the material properties. It is because of the particular geometry in which the material is arranged in. And so as Eladio Dieste would say, you know, strength, it's resistance, not through some awkward accumulation of material, but through form. It's resistance through shape. So therefore, so the Block Research Group is like trying to, you know, upgrade this into a full-on scale building product, where you not only save, you know, significant amounts of material through appropriate structural design and shape design, but you also reclaim some of the space that would have been lost to the floor slab, and you can. So they're trying to currently apply this in one of the demonstrator projects in Switzerland. For those of you who might be interested. So what's interesting here is like both of these aspects of savings of material and space is a direct consequence of the shape. It's not the engineer's domain, it is the architect's domain, where we can reclaim some of these. So it's interaction of engineering principles with the spatial aspects that lead to these kind of multiple benefits. Again, BBC also picked this up, like a lot of these principles are embedded in Gothic buildings, like how to lay out the ribs along the force flow, even how to assemble the blocks and so on. So a lot of constructional information and sustainability, sustainable principles are embedded in previous centuries worth of investigations. and we can also incorporate no more than just that, like we can also incorporate like how the stones were cut and how they're arranged in relation to the force flow in modern day sense. So the so-called art of stereotomy, the art of cutting solids, can be, extended to the cutting foam with a robot. And what that means is that we can get that bench through a series of 7 or 8 cuts. So going from a full block at the bottom right to the formwork for the bench, which was later cast in ultra high performance concrete, is just a matter of a few cuts, and it takes about 3 minutes to get the cuts done. If this weren't the case, if the geometry wasn't designed like this, it would take many hours of cutting away all that is not the bench. So 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 all the dramatic aspects of it, the quality of finish, etc., is a direct consequence of the way it was designed for the machines that will produce. um, and similarly, in this collaboration with Giuseppe Fallacara, who's been training a lot of traditional stonemasons in the use of digital technology. So like here, the stone carries the compressive forces, and the carbon fiber at the bottom, which is a very artisanal skill of the Swiss Italian stone workers, is where there is a lot of tension in the shape. So the shape is kind of pre-computed to have this predominant distinction between compressive forces and tensile forces, and very little bending forces. So and also, like everything that you see in this image, for example, the fabric structure, the benches in concrete, like the flow lines, and each of these showcases are a result of these degrees of freedom that are kind of released from due to the use of this kind of common language of geometry. And what that means is that, like, we as architects could work with the curator. The curator and the curational team wanted to tell about 26 different stories of everyday use of mathematics. So you can see that here at the bottom left, trade and travel, even some somber stories like eugenics, some euphoric stories as the first British flight, and so on. So, and it's a very small gallery of only 900 square meters. And we are able to tell 26 different stories in a very short span, and also improve the dwell times from like a mere 30 seconds to well over 2.5 minutes through our intervention. And so a lot of, anecdotally again, a lot of pregnant women and young children go to this gallery, perhaps because of the kind of lighting, but again, it highlights like how geometry can not only take care of constructional aspects, but it can also combine that with storytelling in a very successful as a successful combination. And whilst we were doing that, we were also able to export or extract the same principles to design this kind of deployable school for refugee children. Before the winter rolled in, like, so it was just it was the same thinking and the same principles, start to finish, in about 2.5 months, where so this steel frame comes on site and it unfurls the fabric, so when it flips open, like, it automatically creates this shape, and it also provides a, a better environment than the current kind of military tents that they were previously using. And we have tried to extend this logic to schools in rural China, where we are using a different masonry technique, like a different historic technique of stone vaulting, and trying to create various types of school spaces, like classes for primary, smaller children, like larger, bigger children, like aggregation spaces, and each one of them is kind of notated through the use of these textures and the size of the vault, etc. Um, again, I will take pause here and launch the next question before going into the next section. Well, let me see here. Yeah, I will launch this. Should architects be taught computer graphics and computer-aided geometric design? Yeah, I'm glad that many of you agree, because usually this is a topic of extreme resistance in, in at least a few other places that have tried to ask this question. And the idea that like we can learn something from computer graphics is almost it's quite considered alien. And so what we are finding is that these kind of techniques that is a mix from like modern day computer graphics, computer animation, computational geometry, a lot of mathematics, not done by architects obviously, but in a collaborative sense, is beneficial not only in like practices like Zaha Hadid Architects, which is a large practice, able to kind of sustain a research group, like which we definitely benefit from this. Like for example, because the right side of this image is taken care of through geometric means, we as architects can focus on the left side of this image, where to place the lighting, which is both structurally aligned, but also helps people experiences, so they can easily navigate through spaces, and the lines which are structurally meaningful also help guide people through the spaces. And so it's definitely beneficial in Zaha Hadid Architects, and also other large firms, like whether it's Foster and Partners or anyone else. But and you can see that it's beneficial in the Beijing airport as well. Like, so these lines which we track in from the early part of design, it's not inserted by engineers later. It's like drawn ahead of time in the designer's models, have downstream benefits. They reflect like on the structural layout of the grid, which are the curvature is definitely beneficial to have thinner cross sections and so on. But at the same time, similar logics are being extensively or beginning to be seeing like extensive use in other building economies, like our colleague in India's Sami Podora. He's been using similar techniques of stone, brick vaulting, etc., to design this library / school, and which has sustainable benefits of not having. It provides cooling, self-shading, because curvature is beneficial to have self-shading, given that no part of 100% of the surface is never fully exposed to the sun. So some part of it is always under the shadow. And similarly, Philippe Yuen in China, like, producing these very intricate mix between like modern day robotic construction technologies of cutting timber, but combining it with more traditional spatial motifs and also constructional techniques of like shingling and so on. And what's interesting about Philippe Yuen is that he first built, alongside Archi Union, which is his company, he also built Fab Union, which is a construction company which imports and develops robotic construction technology. So so that's a kind of interesting growth to see. And they started small, and right now they're building like very large hotels, etc. So whilst we see that like there are all these benefits for architectural geometry, you know, it is still quite expensive. And so there are structural benefits, there are user experience benefits, there are all kinds of like, you know, it preserves traditions and etc. But currently it is expensive both to create it digitally and to physically manifest it. And the reasons for that, are mostly because like the built environment is aligned with the modernist tradition, right? Like it's easier to, so modernism has a 100-year head start, like all the production systems are aligned with making straight I-beams or not, or rectangular shapes, and it's only now that like slowly through the effort of both in practice and also extensive research funding and also industrial funding in the US and also in Europe, that like these new forms of digital fabrication are becoming mainstream, and therefore creation of these kind of geometries are beginning to be very cost competitive. They're not cheaper obviously than other things yet, but they can be because they're in principle they are so much more beneficial. They save material, they're structurally better performing. So we just have to wait for these novel techniques to be commercialized, and they're beginning to be commercialized. And already since we did this in 2016, SOM in the US has now approached the same fabricator in Odense in Denmark to incorporate similar things into their material saving floor slab. Again, you can look it up. It's called Stereoform floor slabs, and they want to incorporate that in like every tower, every floor of a tower that they're designing. So and what's also beneficial is that this company, which used to be 3 architects and a robot, is now a publicly traded company. And you know, it's so they're selling this technology, which arrives in a box, and you know, it's beginning to see things. We are beginning to see that it's getting cheaper. So we are also kind of experimenting or thinking about how importing machines, like just this shipping container with machines, but using local timber, can benefit in the construction of houses and kickstarting a digital economy, which is one of the UN Sustainable Development Goals, is to support local economies and resilient economies. And it also, I mean, it's beneficial for the investor because it avoids importation taxes. And I mean, you don't have to pay taxes on the finished product. You're just importing a machine that can go back. So there's that. Henry and Vishu will also talk about this real world application, like, so not just a image in their presentation. So, but we are already seeing that, like, you know, it is democratizing digital manufacture and allowing countries like Honduras or other Latin American countries to leapfrog the technological divide. Yeah, and then it also provides customization. Opportunities, right? So customization comes for free, right? Like, so it's kind of like whether it's the top right image or the bottom left image, probably consumes the same amount of machine time. And other scale-up businesses, like this 3D printing sculpture that we had done with a London business called AI Builds, is now they are they're a serious startup, like they're receiving investment from large companies. So they are making these technologies available to the extent that, like, you can literally send a part over the internet and they can give you a price and ship it to you, right? Like, so that's what they're trying to do with this mold making technology. So you send a file, they will give you a quote, and you can order it literally over the internet. And there, as I was saying, like at least we are aware of these two big institutes in Europe. Presumably there are like several others in the US elsewhere. That is investing significant amounts of human intellect, but also financial backing into making these new technologies that were experimented with in the last decade to take them mainstream. Oops. One example with ETH Zurich is this formwork technology, which is a lost formwork technology that we worked with them to build this concrete shell in called Knit Candela as a homage to Felix Candela and his geometries. Again, Vishu will talk about these in greater detail. But what was interesting was that like the entire formwork was knitted in Zurich and weighed only 55 kilos, and it was sent on a commercial flight in as cabin luggage, and then subsequently hoisted and pulled over and tensioned, and then concrete was cast onto it after. And to produce the final outcome in a matter of start to finish. Again, it was only 2.5 months. And what was interesting is not only we were able to collaborate pre-corona times across digitally in between London, Zurich, and Mexico City, where Architecture Extrapolated, the fabricator, was doing stuff in Mexico City. Block Research Group was in Zurich, and Zaha Hadid was in London. So that was one significant benefit, but also all of the materials, all of the things that came, this sculpture was brought into this courtyard pit, which is 6 meters below ground, through that door that you see there. So and then we also demolished everything and like took it away. Right now there's nothing there. So that's one of the key benefits of like considering you know, the performance of shape ahead of time, like construction, structure, and also expressive quality. Like, so because it was knitted, all of these patterns come automatically. It's like the same technology that's in the Nike Flyknit shoe that is now being made commercially available again through the efforts at ETH Zurich. And lastly, efforts underway to make architectural geometry less expensive to create digitally. Why is it expensive to create digitally currently? Well, because there's a lot of effort in knowledge acquisition. You know, it means several hundred researchers have to literally dig through previous centuries of information and upgrade it through computer code and mathematics and so on. Like my colleague at Block Research Group, who is now a professor at the University of Pennsylvania. Masood, like so this piece of research, like literally unearthed theorems from James Maxwell in the 16th century and kind of upgraded that to understand the structural stability of these kind of skeletal structures, amongst other things. And what we found as ZHA Code in our research was that that structurally meaningful principle can be extended to also have some constructional information. So for example, all of these complex joints can be made from flat timber sheets and flat metal sheets just by bending these hexagons. And again, all of these are like not they're just geometric principles like that allow for not only structurally meaningful, structurally performing shapes, but also ensure that like these can be manufactured or constructed using flat sheet material like this. So the property helps that you can bend a sheet of wet bend a sheet of ply, and then make very lightweight kind of formwork at least. And also allows for a spatial extension, considering the spatial effects of these. So there is a lot of effort needed, like you have to experiment design-wise, you have to experiment physical prototyping-wise, and you have to experiment like in acquisition of knowledge. And how this is getting cheaper is through code. A lot of these research groups are putting out like like just code frameworks, and also examples and so on. Like, so by now, the entry point is very relatively much lower than where it was just 5 years ago. And a lot of examples and a lot of code is available even internally to Zaha Hadid Architects. Like, so we as researchers, we develop, let's say, the left end of this, like so-called framework, and a large bulk of it is now available to be used by other users in the company. So they don't have to go through all of the same efforts to acquire the knowledge. And so in this sense, we are beginning to see parallels with like the kind of Gaudi economy, right? Like where there was instrumentation, and there was also like these manuals available, like made available by mathematicians and so on, how to construct, how to draw things. And so this is the digital equivalent of that. So it is getting cheaper, so there's much hope and much much reason for optimism that things are going to get really mainstream relatively quickly. For example, like Philippe Bloch himself did his PhD in MIT 10 years ago, or a bit more, and this geometry like would have taken him like several, maybe understanding the structural stability of this kind of geometry and how to even draw this geometry was his entire PhD. And in this joint collaboration with Philippe Bloch and Zaha Code in Shanghai, students were able to pick that up in a matter of a week. Not only draw this, but also make 3D print it and assemble the model and make it stable through the use of this red string. So there's no glue involved, right? Like, so you cut that string and everything is going to come down. So how do you draw the geometry such that they're in this kind of structural balance? Like, so that was Philippe's PhD, which students were able to acquire in a matter of a week. And we are also then subsequently able to incorporate some of the findings from the workshop back into our software. And now we are trying to, extend those kind of shapes and through our own models, like 3D print them, and you can see the cable there, not yet working. But we also physically made one such partial prototype, but eventually when it's complete, it should be something like that. So again, held together by a tension tie, everything else in compression. So things are getting cheaper digitally, physically, and to the extent that like students also, like they were able to incorporate, like in this kind of stakeholder participation game, that they were able to incorporate these kind of novel geometries, which can be hot wire cut. Again, a reminder, using these hot wire cut technologies, and they were able to acquire the necessary knowledge to create the shape on the left, but also go to the factory, just 3 students, and work with the robots and construct this proof of concept in a matter of 3 weeks. So this is very encouraging to know that like all of this that would have taken several years of effort is now beginning to be accessible, and to the extent that we are now trying to work, suggest at least that this old catalog needs to be upgraded with new so-called non-prismatic solids. So prismatic solids at the bottom and non-prismatic solids at the top, sorry. So I will end there and leave it to Henry and Vishu to kind of give you far greater details on how these are applied. But I would like to just end with this idea that architectural geometry, which is upgrading knowledge from several centuries ago through the use of computer graphics, computer geometry, computational technologies, is actually much better, and it is getting cheaper and becoming mainstream. So it's better structurally, it's better ecologically, it's better spatially, and we are beginning to see its mainstream contributions to things like cultural buildings, or large unique buildings like stadia, metro stations, so on. But they're currently underway, and so they're a bit confidential, but we can kind of suggest or at least show glimpses of it, like this stadium that we're building in China. Yeah, so so with that, I can take questions. And and Vishu and Henry will will show further applications of these in both in two domains, not only the unique buildings but also in the kind of residential mixed-use development, including a live project in Honduras. Yeah, thank you very much for your attention. And
thank you. Thanks for the invite. Myself and Henry would be presenting this session on architectural geometry and habitat. We are both designers at ZHA Code, and we also teach at the Bartlett School of Architecture, where we have a studio together as well. The structure of the presentation is as follows. The first part of the presentation will focus on architectural geometry and how it is pursued through research in both practice and academia. And the second part of the presentation will focus on the habitat and how computation and stakeholder participation is kind of integrated into the housing projects we do. Brief introduction into the group. ZH Code is Zaha Hadid Computation and Design Research Group. It was founded in 2007 by Shajay and Patrick Schumacher and Niels Fischer. In its existence over the 15 years, it aimed to, not 15 years, 13 years, since 2007, it aimed to create the interdisciplinary collaborations through technology demonstrators, and as well, and subsequently getting more and more involved in projects. So when we say interdisciplinary collaborators, we create these kind of installations, which are, this is in Copenhagen, where we are collaborating with the technology to make this fabric movable, and then kind of displaying code on top based on how people would interact with it. It also expands into facade projections. This was a project in Karlsruhe. It's again a collaboration with Disney Research Group and Andy Lomas, who was a computational artist. We also do technology demonstrators on the structural side. Look, this one is the Beijing Binale in 2013, looking at the topology optimized shell structures. And other mandate of the group was to create a list of collaborators or have a wide range of collaborators so we can call upon for different things, varying from 3D printing and robotics, data and machine learning, creative coding, manufacturing, engineering, etc., whilst also maintaining or developing our associations with institutes such as Block Research Group, Architectural Association, which Shajay already mentioned in his presentation. More recently, since 2018, we have an association at the Bartlett, and through visiting schools, we also develop networks in India, Mexico, China, etc. Uh, the focus of our research sits at the intersection between these two ends, what is design, what things valuable to architectural design, and on the right side on computation, or what computations can do. And for this, we refer heavily to mathematics, computer graphics, and game theory. And the intersection of these two is where our research lies. As as we saw through Shajay's presentation, we seek to have a historic continuum to learn from the past and stand on shoulders of giants and build on top of it. When we say learning from the past, it doesn't only mean the architectural side. We also look up at the historical side on the mathematics, game design. In this case, on right, you can see Lionel March. And on the left side, most of us would be familiar with is Antonio Gaudi. We look at the design precedents or design technology precedents, even historically through which is available in Renaissance. This is Filippo Brunelleschi for using design technologies to build dome at Florence. There are statics related design technologies here, physical form finding of Antonio Gaudi and Frei Otto. We also look up at mathematicians such as David Huffman or computer scientists like Eric Demain or Joseph Albers at Bauhaus, who were looking at folding paper and trying to give strength to geometry through folding. We look at engineer architects such as Eladio Dieste, bringing tectonics of how adapting to local context of tectonics of brick and bringing performance through geometry. Here again, the curvature is adding to structural stability. And also other architect engineers such as Felix Candela on the right, who focused most of his entire work on a particular geometry called hyperbolic paraboloids, a specific subset of ruled surfaces. And Pierre Nervi on the right here, also bringing in rationality of construction, not only geometry, but also bringing in rationality of construction and statics into the mix. So learning from these historic figures and combined with maturing computation tool sets in the architectural industry through architectural geometry book by Helmut Portman or computation statics framework by Block Research Group, Axel Killian, etc., combined with other computational frameworks developed by geometry groups, again in TU Vienna, at ETH Group in the Interactive Geometry Lab, Keenan Crane at Carnegie Mellon, has matured the computational framework to bring it closer. So we are now able to express both statics, fabrication related constraints, environment constraints, and early stage shape design. And that is what is called architectural geometry, to make it visible in shape, structure, fabrication, and more recently, other performance factors like environmental performance, solar data, etc., into the shape design and influencing it. So most of our research situates at this level at early stage design. So where there is flexibility to change geometry to adapt to these constraints given by set by the designer. So these geometries are geometries of physics. They relate to structural performance of physics and also have a rationality in fabrication. The goal of the research in architectural geometry is to augment designer intelligence. It's not to replace the human, but to augment the human intelligence with these tool sets, so you're making an informed decision. Typically, the group involves in these three domains, which we will touch upon each individually. One, on the left side are technology demonstrators. We also have academic wing in the group, where most of the researchers in the group are also teaching at the AA or at the Bartlett, and eventually combining these two research and feed into architectural projects. The subsequent presentation will touch upon all the three aspects and how they feed into each other. The first part of it is learning by doing. So the academic setup, how we carry out our research in an academic world. As previously mentioned, we have academic collaboration at the DRL and at the Bartlett at the architectural computation, as well as architectural design courses there. We have done over 40 plus workshops over the years, where we try out different things in each of these workshops to develop our understanding in research of geometry. Yeah, there are certain slides which will be overlapping with Shajay's presentation. In this one, again, a workshop in India where we're trying to physically understand or building an intuitive understanding of how paper is folded by drawing crease lines and giving it the physical force to bend. But this is a physical way of understanding things. But when it comes to computation, we need to kind of go the other way around. You need to understand what makes it, given a geometry, can I make it go back into a flat sheet? That you need to reverse engineer this, and you need to learn the computational aspects of it. And then once you have it, you can write a small snippet of code. Again, this might be about 15, 20 lines of code to make things go back into a flat sheet. That's what is happening on the right. If I play the video again, you'll see that initially it doesn't go in, it unrolls not into a flat sheet, but after a few iterations of computation, it's able to go back into a flat sheet. The logic here is when you're seeing things changing into green, that means all of these polygons are becoming planar. And when the vertices become white, that means the angle there is 360. That would make it a flat, you unroll it into a flat sheet. So this principle, of knowing this principle and trying to implement it in a computational framework is what we through what we call learning by doing. So we have to first understand the physical phenomena, then dig deep into this research papers to understand what the logic of this is, and then you can implement your own tool to explore the design domain of such shapes.
This is also a relatively good example of enabling early design exploration for others in the group. And what I mean by that is people don't naturally understand how to make a shape that is unfoldable, but many people could get 50 to 75% of the way there just by modeling it. It sort of looks correct. And so what we're doing here is simulating a process that gets it that remainder 30% of the way there to make it unrollable, which means that we can capture a larger percentage of the staff to be able to think about projects with these types of shapes. So if they start out with something that has a sort of red flanges on the underside, that's already in a good state, right? And then we can get them the rest of the way there. So this is one of the ways that we also interface with the group.
And also the rest of the office. There was a question about how design technology is transferred to the rest of the office is by transfer of these tool sets and the computational knowledge behind it. In a similar domain, we again playing with this Jenga. Everyone knows this game. Trying to we were trying to have like a overhang problem, the maximum overhang problem. Try to keep things in stability while achieving a large overhang. You can now recreate the same in digitally through rigid body physics. So one is to understand the computational tool sets available out there to recreate this. And that also involves, that's also part of the research through our teachings. We tried students to look for these papers and understand the technology behind it, and then use it in early stage design. Similarly, we also look at examples at the digital examples, playful examples at the computer graphics. This is a subdivision, dynamic subdivision of an input surface, and then a circle packing of it. When you look at it first time, it might not have a direct application in architectural domain, but it is to build this intuition or understanding of the domain first, and then eventually through, because we are all interested in design, we can find application in architectural domain. So applying the same logic here in the facade design, you can see the same logic working here to subdivide where there is a lot of curvature, highlighted by black and magenta here, and where it is white, it's almost flat, so you can have higher subdivision or bigger panels. Similarly, building understanding of statics or graphic statics, we look at heavily at block research group in this domain to understand the logic behind given a network of lines, to understand through graphic statics that there is always an equivalent network of lines of the same number, what is called the force diagram. And if the network given on the left is to be stable, is given visually correct by having a closed polygon on the right. So if the three edges here form a closed polygon, in this case a rectangle on the right, that means the point in the center is structurally stable under the given set of forces. So one is to understand the logic, then is to explore the same logic through a design tool set. So this is exploring the same idea of form and force diagrams, but in this case also inputting a designer constraint of, if I change the input geometry, how does the form and force diagram change, or developing an understanding of that. Once you have this understanding, you can build up the tool sets to integrate it into a designer domain or the designer environment. The office uses quite a lot of Maya. So we try to integrate our tool sets in Maya so that the designers can interact with it and develop geometries, in this case, which are funicular shapes, which are in compression, and developing an understanding between forces and the resultant geometrical shapes. So once you have the tool sets, the next step is to kind of use it in the design domain, try to build up structures. This is again explored in collaborative workshop with Block Research Group at Shanghai, where students were exploring this polygonal modeling combined with graphic statics or thrust network analysis to build up geometries, and then subdividing them into panels or small blocks, which all stand in stand through friction. And this is an example of one of it, trying to do a spiral staircase. Students are building small scale models to understand the logic of construction and how it could be built. As you can see on the right, it actually collapsed. This is a way of learning, and also to prove that the geometry is actually trying to build in pure compression and standing only in friction. The same logic applies to this geometry here as well. The whole structure is held together by this tension ring, which is a pink string on the top. If you cut it, all of it would collapse, like you saw in previous video where the staircase collapsed while they were removing the scaffold. So these are the understandings we want to build through research and also inculcate into students to explore the design domain given by such a tool. Yeah, similarly, like this is looking at form finding in a physical domain, not through graphic statics, but through what we call as particle spring systems, where you're trying to inculcate principles of curly kale, how it grows naturally. So here there's a differential growth. The growth is given by the color. And then you add in fabricational rationality on top of it. In this case, trying to make all of the hexagons planar. So all the faces of the hexagons are eventually planar. Why it is needed to be planar? Because we wanted to make it out of hot wire cut blocks, foam blocks, which are easy to cut. So as you can see here, each block is cut through, because all of them are planar cuts, you can just pass the foam through a string of hot wire and the block is made. And as you can see, each block this is almost real time. Each block takes about a minute or two to make. And the overall assembly, the overall structure had about 160 blocks, which was all produced in 3 to 4 hours of 3 to 4 hours time. Yeah, we try to build in the workshops or in this to build the prototypes together. So the students are also involved in the assembly and the fabrication part of it, not only exploring the design domain, but also having an understanding of how things are built. Again, this is like 10-day workshop. The assembly of the cutting of the blocks took about 2 to 3 hours, and the assembly was again 4 to 5 hours. Similar logic. In this case, we were exploring the geometrical principle of Varigno's theorem, which kind of given a quadrilateral and two opposite vertices on the diagonal, in this case A and B. If the offset from A is the same as the offset from E, you will always get a quadrilateral which is planar. So the quadrilateral HBDE is always going to be planar, irrespective of how you change the quadrilateral shape. So exploring the same principle in 3D, given an input volume, you can always extract planar quadrilaterals, which can be cut in a laser cutter or a CNC router. Again, this kind of suggests has an implication in or structural influence from what is known as graphic statics. The shape is in compression, but our research here was to bring in fabricational rationality and exploring the design domain provided by that. This was produced in India, where at that given time there was no laser cutter. So we had to adapt it to local design fabrication tech we had there. So a laser cutter was here replaced by 3 humans trying to map out the cutting platform, one of them drawing the shape of the profile and then cutting it. So there are tolerance issues. This is picked up in how it was assembled because of there was no labor involved. It was all students putting this together. The geometry, because it was bent metal, it would take up the tolerance while we are building up. And also the tolerance of fabrication was input into the design itself. So the metal, because it was going to be produced by humans, were scaled down a bit so we can adapt to that tolerance while constructing. Exploring the same logic further, in this case, we got rid of the metal connectors in this and built purely out of bent wood. Exploring the same strategy of unrolling a given geometry into flat sheets, which can be laser cut. So you can see all the sheets kind of unrolling into flat sheets. And in this case, because it was all made of timber, we had to explore a new connection logic of these kind of teeth connectors. And this was the sequence of production. So you have a CNC cutting the profiles. It was produced then put in water to give the tension or the curvature needed to bend, and then assemble one of the nodes. As you can see, it is quite light, and then locking them together with human winding and locking it together in place. This is another research domain we were exploring. We wanted to do this using robots, but to understand the logic of it, that's why you're seeing on the video on the left here that it was done with one hand. So just to try to replicate what the robot would be needed to do to understand the logic and the sequence of this winding, and then subsequently develop the tool sets on the right. So the digital representation when the workshop was done wasn't existing. It was done manually to understand the process. and then subsequently developing a computational tool set to explore it, and then eventually to try and make it with a robot. Previously, we also mentioned a bit on the curve crease folding. This is applying that in a larger domain, in this case, a compressive shell. If it works on one Y module, as previously shown, it can work on a assembly of multiple panels. You're just scaling the computational time, but the logic remains the same. And as you can see, when everything becomes green, all of it can unroll into flat sheets. And that is how it was produced. So you unroll them, you cut, in this case it was metal, you cut them with a laser cutter, and then you bend them back into shape. Again, all of these again was explored by the students. But in this case, these molds were becoming formwork for concrete. This is where we need skilled labor. Skilled labor was used to cast concrete onto these folded molds, and then assembled on site using metal connectors between panels, as you can see on the right. This is a work in progress of the shell structure. Similarly, as you can see, the scale of application keeps increasing. We are kind of growing as we become more and more confident with the tool sets. This is another example of a shell structure in India, and the similar at around the same time in Mexico. Again, all of these are through 10 to 12-day workshops. So the construction period is also very concise and very small. This brings us to the second aspect of our how we work within the group is to collaborate with technology collaborators. They bring in the technology, and we try to experiment through design how to explore and understand the technology. This can be through 3D printed technologies or high resolution 3D printing technologies, in this case for Stratasys. And the design domain here was for a chair. The technologies which were tested here was topology optimization in combination with high resolution 3D printing. Again, in the scale of a chair, we were experimenting with stone, combining stone with carbon fiber. And here the material is actually performing where stone is, the structure is predominantly in compression, and wherever you see carbon fiber, the structure is predominantly in tension. So this was in collaboration with New Fundamentals, Giuseppe and AKT, trying to, again, exploring the tool sets we showed prior, which was like the Maya Vault, exploring compression tension shapes, and then highlighting them through tectonics of materials. Similar, another dining pavilion. Here it was collaboration with 1-to-1 and UAP. There were two prototypes, the first one with 1-to-1 and the second with UAP. This was looking at frame structures, trying to minimize the torsion or making them planar. Again, as you can see, taking an input geometry and trying to rationalize them so that it can all be made up of developable surfaces. In this case, what we mean by developable surfaces is that it can be unrolled into flat sheets. So all of these loops, again, same logic as previously shown, unrolls into flat sheets, so they can be cut with a laser cutter and quickly put back into shape. This is a built prototype. This is the second version. It was a dining pavilion, was exhibited in Miami Art Basel. Another technology demonstrator, in this case in collaboration with AIA Built, a 3D printing company, robotic 3D printing company, and Odico Formworks, who do robotic hot wire cut formworks. So because it was going to be printed with a robot, the design exploration here was differential growth of a curve, because the input to the robot eventually was going to be a curve. So we wanted to expand a single curve as much as possible in a given domain or a given shape, and a differential growth algorithm was adapted here to also perform or correlate to structural performance. As you can see, the density of the pattern is increased towards the boundary because that is where the high structural forces are, and the density of the pattern is reduced in the center of the geometry where there is less structural force action. So is the video repeating? The second aspect of the project was to create the formwork on top of which the robot was going to print. The formwork here was done with hot wire cutting, and because it was a hot wire cut formwork, it had to be in the domain of what we call ruled surfaces. So in this case, it had to be, if you cut a section through the geometry, it had to be made up of a line that is a ruled surface. And then once you have the geometry in place, you can extract blocks which can be wire cut. We have to also incorporate ideas of fabrication in here, trying to understand how the robot would print. In this case, looking at features of rotation. But as you can see, the block had to rotate multiple times. In the second instance of the pattern, it had to rotate incrementally. But eventually it was done in 3 parts. So the rotation of the robot and the formwork was slow and gradual, so the printing can adapt to it. So this was how it was printed. And you will see in a bit like the physical manifestation of it. So the formwork here is coated in so that the plastic doesn't stick to it. And this is a bit of close-up view of how the robot was printing on top of a wire cut form. So this is what you see on the right is the formwork, and on the left is the built prototype, which was split into 3 parts. So it could be shipped to Milan and assembled in an exhibition there. Another technology demonstrator is this one was revisiting Candela's hyper shells. As you can see on the left, it was a solid shell in concrete. We were revisiting it as a grid shell, which was topologically optimized. The color here represents performance. Wherever it is pink, there is high structural action, so the density and the density of material is high, and where it is blue, the structural performance, or you can remove material there, so it is the thinnest wherever it's blue. This continuing on our reinterpreting Candela's work, we were in this case in collaboration with Block Research Group and Architecture Extrapolated. We were questioning the form needed to build structures like the one on the left, a concrete shell by Felix Candela. We wanted to minimize the scaffold, and the scaffold here was given by a fabric formwork, a technology developed at the Block Research Group, and then cast in concrete by artisans or laborers in Mexico. So it's kind of bringing together design technologies at Zaha Hadid Architects at London, combined with digital fabrication technologies at the Block Research Group, also inculcating structural performance into it, and in combination with the skills and artisan skills of the laborers in Mexico. So this video is highlighting how the design was developed and how the fabric, because it was fabric, it had to be a minimal surface, and it was produced using a machine and the PhD project of Mariana, who was developing her PhD thesis on this fabric formwork. And it was the whole design to fabrication process was about 2.5 months, right from design to production. This is the machine which produced the formwork, which was packed into a backpack and shipped into Mexico. As you can see, this is Mariana on the left, and they took it in two backpacks, 55 kilos of fabric formwork, which was then unrolled and erected in Mexico. So this, although, yeah, we needed a certain amount of like false work just to hold the edge beams in place while we erected the fabric formwork. You can see cable net was inserted into it to give the right tension. And you will see in a second that how the whole of the fabric was pulled into shape to get the minimal surface. Just tensioning of the geometry. Yeah, there was an idea to reduce structural material as well, concrete. So in this case, there were balloons inserted in between the fabric voids, as you can see here, to reduce the weight. And then once the balloons were inserted, a special mixed concrete was used, which was quick setting to stiffen the fabric. You can see that was the first coat, and then subsequently finished by the labor and artisans in Mexico. The whole of this construction was about 1 to 2 weeks in the courtyard of MUAC in Mexico. Some views of the technologies used in the project and the built project. In this case, the formwork is lost. It becomes an expression of the design of the sculpture here. It became, so all the lines here, the patterns were also expressing the forced lines in the geometry. Through these technology demonstrators and our research in academia, we also are building up a computational framework, which we keep adding to. Everyone in the group have an understanding of code, and everyone also write code. We favor the first principles to understand and develop code. So as you can see, this is Phillips Bloch's trust network analysis. It gets compressed into 3 to 4 lines of code, which is exposed to the user. But to understand the first principles, each of these, you have to expand it into like about 200 lines of code. Over the years, we have developed the core framework, which explores different aspects from creation of geometries, incorporating static information such as spatial structures, funicular structures, minimal surfaces, and adding rationality of construction, in this case, rule developable shapes, 3D printing with concrete, curved crease folding, and more recently, we are also adding in digital fabrication, cost and analytics, and also timber joinery and tectonics. This is like the framework diagram, because eventually these have to, even though they are standalone frameworks, it has to make into designer environments, and so that it can be pushed through the office for others to use. So the predominant use of software here is Maya and Rhino, and more recently for visualization, we are also using Unreal, and also for gaming technologies. Some of the tool sets, I'm not getting into detail here on fabrication. This is looking at graphic statics, and then also robots and inverse kinematic change. So at an early design stage, you have the feedback of how it can be, if the geometry is feasible to produce with a hot wire cutter or 3D printing, etc. We also have to develop tools to interop between softwares, going from Maya to Rhino or Revit. So this is like another aspect of the framework and technology we need to develop within the group. More recently, we have also looking at incorporating environmental performance, in this case, solar analysis. But as we are interested in early stage design, we want it to be very quick. Generally, these calculations take a lot of time, but we are interested in an 80% solution. That means trying to inform at an early stage with fast approximations. So you're already in a domain. While exploring design, it needs to be quick feedback. So that's why in this case, the solar analysis, we have adapted a tool to give quick feedback. So it's almost real time while the designer is changing or updating the geometry on the left. You're understanding what is the cumulative radiation throughout the year. These are fast approximations. It is not. It can be made more accurate in later stage design. But when you're looking at conceptual stage, even an 80% accurate model is good enough. Through the development of all of these computational frameworks and research in understanding of technology, we are now seeing applications of these in large-scale projects within the office, be it in museums and galleries or stadiums and arenas. We are also doing metro stations. It's also similar frameworks are used in master plans, building offices, etc. I'll give a few examples of a couple of them. This is the Mathematics Gallery at the Science Museum in London, where we were exploring the domains of lightweight structures, how to organize the space, and the hot-wire cut, robotically hot-wire cut concrete benches. So the the concept of the gallery was to situate this based on understanding from the curator, was to place this Hadley Page aircraft in the center of the gallery. So we were using simulations of airflow around it to be the guiding principle for the gallery. So all the objects, all the circulation and space planning was based around this flow field you're seeing in pink here. You can see the first step was to develop a curatorial set in conjunction with the curator who wanted to showcase application of mathematics in day-to-day life. And he wanted to explain it through stories. Each line is a story here, and each line has about 10 to 12 objects. As it was a collaborative setup, the object list kept changing over the period, and we had to set up a computational tool set which adapted to the changing object list and the changing location of stories. As you can see through this animation, that the stories kept changing, the location in the gallery kept changing. So it had to be a flexible way. We needed to come up with a tool set which allowed for that flexibility. The central piece, which was initially kind of trying to capture the flow field behind the plane, was a minimal surface. Again, here kind of extending the design history of Frey Otto's soap bubble experiments, physical form finding, but now through computational tools. Using the computational method, you can try. First, we were exploring minimal surface, which was given by equation, and then subsequently rationalized to be actually built with a fabric like to be built with fabric and edge pipe, which was made up of metal. So these were some of the tool sets which were developed for the project. So you can see eventually it was built in 3 parts, so 3 objects. So we make small scale prototypes within the group to understand the fabric and seam layout, the geometry you can see on the right. And understanding of all the build prototypes which we had through our technology demonstrators and through workshops we were able to actually gave us an insight into kind of push the manufacturing or the engineering aspects here. As you can see on the left side is the conceptual geometry. And the first instance of what we received back from the engineers was a triangulated geometry and the loss of curvature. But because of our experience in building the prototype on the right, but also additional knowledge we had built through prior prototypes, we were able to push back and somehow negotiate with the engineers to be much more closer to push the geometry to be somewhere in between what was given by the engineers and what was the design intent. The same can be thought of the seam layouts. The first instance of the manufacturer was this layout at the bottom, but because of our understanding of the tools and the constraints of fabrication, we were able to push the fabricator to come up with a much better seam layout, again, in collaboration with the manufacturer. So this was the built one, and as you can see, the seam layout kind of is more geometrical in this sense. The third aspect of the feature set in there was this hot wire concrete benches. It was exploring, because it was to be cut with a robot and with a wire, it was exploring geometry in the domain of ruled surfaces. So you can see a block, how a block is cut away to create the geometry. So there were 16 benches. Because of each of the formwork for each of these, because of the technology of hot wire cutting, took about 3 to 4 minutes to cut. Each of them could be unique. So there were 5 types, but all the 16 benches were unique because of the technology we were using. It didn't matter to the robot, like the construction time or the production time didn't change, as the principle was what was more important than the actual geometry being similar. So this is the built prototype. Once the formwork was built, it was cast on high performance concrete. It's about 2 to 3 centimeter thick. So this also helped in saving material. So the formwork is actually inside this, which made the whole block very light and shipped into London from Odense and assembled on site in three parts. So if required, this can be disassembled. You can split them back into 3 parts and take it elsewhere. This is another recent project we have been involved in. This project in Xi'an. It's a football stadium where we are applying the same understanding of architectural geometry into large span roofs and facade systems. It was a competition in March. It's a 60,000 seater stadium. Helped to hold the Asia Cup in 2023. It's getting into construction. The basement is already under construction, but the architectural structure would go into construction early next year. The idea here was to explore all you see in Oden is actually terracotta tiles. So breaking up of these geometries into panels which are feasible to produce is where architectural geometrical technologies were used. Another application was to find these cable net roof structures, as you can see, and in negotiation with the engineers. This was an early stage competition, but now we are able to get rid of the truss in the middle basically in collaboration with the engineers and our tool sets. We are able to make this cable net even much more thinner and get rid of the truss in the middle.
So in the same way that we were looking at the sort of soap bubble of the Science Museum by making digital approximations, making physical approximations, there's an emphasis in the group on making in both worlds, both analog and digital, because it allows us to see things from a lot of different perspectives. It allows us to test things. It allows us to fail. And it allows us to sort of move forward from that. It really doesn't matter where we start, as long as we sort of just get started, and we'll learn something along the way. And in the roof in this is no different. You know, it started off looking fairly conceptual and became very dense at times, and then became very loose at times. And we worked through the patterning and cable directions in tandem with the engineer, trying to articulate the geometry and the primary lines of action along it as part of, you know, an engineering discussion. And we were able to, you know, engage in that because we are testing out things in parallel with them. So it never really becomes a sort of confrontational discussion, but rather becomes a, look, we're testing it out in this way, and you're testing it out in this way, and there's a shared language that happens at these points. And that's what makes it a really fruitful discussion. And it's a very humbling to sort of continue to make things and know that many of them will not see the light of day, but that you're exploring the domain of what is possible, and that within that domain, there will be valid results. And that's sometimes difficult to sort of take on, is that you may not know the exact answer, but it's sort of an open-ended question. You just have to systematically go for it and methodically test what you believe to be the right trajectory. And then you come to a resolution. There could have been another resolution, I'm sure, but the resolution you came to was methodical or systematic, and therefore it is transferable in a scientific way that someone else can repeat it and still do the same. So this is one of sort of the principles of the group, is to keep making things digitally, testing things digitally, tinkering, breaking things, failing, and then continuing on to make more and more successful and more articulate results.
Yeah, and all of these, yeah, the architecture, like the geometry was the aid, and because it was visual, we were able to communicate with the engineers, with the fabricators, etc. And more so recently, we are also finding the application of architectural geometry in what we call computational housing and habitat, which is the second part of the presentation.
So hello, everyone. My name is Henry. I'm actually coming to you from just outside of Baton Rouge, Louisiana, while Vishu is in London. I missed a flight due to the hurricane that just hit, but I'm happy that I can sort of join you today, and that the panel is also today and not a few days back. I'm going to be talking a little bit about our computational housing domain as it's sort of grown over the past few years. I am from the States. You can probably tell from my voice. I grew up in Louisiana, got my bachelor's degree, my license in Louisiana, and worked for several years before my wife and I decided to make a life change and sort of go to graduate school in London, and that's where I met Shajay and Vishu afterwards, and have been with the group since 2013. What's really been fascinating with the group is how it has shifted in sort of our discussions that were more tool oriented or more the making or enabling of others, and are sort of bringing on more and more responsibility to help in delivering projects by ourselves as a group. And that's been really, really useful to grow skill sets globally for everyone in the team. And also has been really worthwhile to test out a number of things, both, you know, that we're exploring academically in a very real research and practice sense. So computational housing, we'll get into the term a little bit, but the group has taken on more and more sort of competition roles and discussion roles within the broader firm to assist in sort of looking at some of the themes that are facing us in housing today, meaning things of density and also of social equality, economy, and sustainability. So there are looking at a number of themes, a number of technologies, and a number of ways that we're addressing them through different spatial systems. So the way, a little brief look at, this is not what we're talking about when we're talking about density. And often we hear people use the term of efficiency, and this is sort of what comes to mind, is that we're going to cram people inside of something, and 10 to 12 people, and the only thing they have access to is air and maybe not light. So, in COVID times, we know this is like a terrible thing. We knew it was terrible before COVID, but nonetheless, often this is sort of a default condition. This is what we are going to avoid, is efficiency. What we want is effective housing, and effective housing means slightly different themes that we have to take on. So one of them is porosity and how we develop sort of airy spaces that can bring in light, but also looking at ways of how we actually space plan these things so they can have interesting spaces or spaces that surprise us, in this case in unit habitation, having double height spaces, or and there are also concepts of how we activate the social realm, which is maybe something that is not so, is the part of housing that people sort of least, is most known for or infamous for, in the sense that the public domain needs to be activated in multiple ways, both spatially and operationally, to make them effective. There are other things that we're interested in too as a group in computation, and thinking about sort of first principles in physics and sort of rigid body physics and the stacking of things and how stresses transfer, and if we were to do something which is low rise or that has sort of cellular nature, how that can be used to have minimal footprints but still have sort of maximum projection, so to get the least impact on the ground with the most impact in the air. So these types of things we're trying to study. At the same time, we're looking at sort of material aspects and material technologies, and this is an example of Lustron House, like a post-war housing project that's all metal framing. That didn't, many were made. You can see the bathroom on the right is all metal. So there are a lot of technologies that are sort of coming to pass. Also this is Edison with a single pour concrete house. And this type of thinking about how we make a house out of concrete still persists today. And the underlying theme of this is, what is the tool that's going to deliver this concrete? So in Edison's particular case, it was about trying to get the concrete as close to the top without it sort of separating. So he has a patent here that's sort of addressing that particular thing, in addition to the formworks that are necessary. So there's an emphasis on the making of a tool almost as much as there is in a house, in the way that Vishu presented the sort of Brunelleschi horse that would hoist up to be able to erect the dome. We're interested as well in prefabrication and cellular and modular construction, and this is a case from Jean Prouvé entitled Maison Tropical, which is seminal in the fact it also has a very small mast that a very large canopy is erected over, and it's very light and delivered via airplane. Who wouldn't want their house delivered on an airplane? But nonetheless, it is starting to explore delivery systems in housing, in the same way we would see out of Buckminster Fuller doing the same thing, but for light skin structures and pulled stretched floors and tension, and how much does your building weigh. There's also an emphasis in our work in how we're thinking about these things as products. As in, are there elements inside of them that can become cells of their own, in the way that we would see Buckminster Fuller again with patents for sort of bathrooms and bathroom fixtures, starting to think about industrialization in the housing realm. So modernism, Walter Gropius here, we are starting to think about things also as kits. Digital kits, physical kits, prefab kits, any type of kit you can think of. And in this case, Gropius is thinking about spatial kits. They're not really kits in the sense that you would order this and then erect it, but rather it's sort of like spatial blocks, and you're able to sort of combine them together serially, and you have a house. So this one, Serial House, again with Adolf Meyer. But these are ways of thinking about spatially how we plan for things, and they may not seem sort of groundbreaking in that sense, but in the way that we're looking at the gaming and configuration of these spaces in the next few slides, these become actually foundational on how we think about discretely pulling apart space so that we can put elements into the space and reconfigure them serially. So in this sense, there's a uniform grid, and from that we can get 4 houses. Other ways of thinking about spatial representations and kits, what it means to be cellular. So Lustron House is the metal house is a very good example of like how many things can be delivered and put together, but maybe not necessarily come to pass. How many people live in a Lustron house today? Though it was a successful business at the time, it is no longer around. So how do we get prefab off of the ground a bit more? This is sort of something we're grappling with as well. There are other ways to think about prefabrication, and one of them we're exploring sort of with the academia and the Bartlett is about trying to sort of look at these kits and exploit what is within them. So how many different typologies of things do you see within this image? Easily a dozen types of different things that come together as a mosaic, capturing different awnings, partitioning systems, canopies, terraces, awnings, bridges, all of these types of things can contribute to the built realm. And so our exploration is to start to think about how we exploit them. And so this is an animation called Townscaper, which is not sort of in the computational sense a replication of elements, but is rather sort of dynamically changing or adapting like stylistically like elements to combine to make a composition. And I think this is where we're sort of most interested in. So while computation and design as a research group has both parts to it, both the computation side and the design side. And the design side often is seeking to exploit things or to explore things, or they may not have the right solution to break the computer, so to speak. And this is a good sort of example of that, is that it may be difficult to see how all of these things might come from the same lineage, but nonetheless they are. There are examples of this in the past of sort of thinking about housing in terms of types or kits, or in this case, class systems for working. This particular one is in Hornsey, but in the way that we deploy like bay elements, but with variable kits to express them for different purposes. In the same way, you might want to order a house and have a different add-on. You may want a larger garage or a larger portico or a more expansive porch. And all of these things are valued by the audiences that want to buy them or procure them or to develop them and sell them to us. So it's important that we sort of know this and engage in this activity, in the activity of addressing multiple audiences, but at the same time addressing multiple desires and competing desires sometimes. So one of the ways that we do this is by trying to break apart geometry into discrete sort of elements and trying to combine them back together. And we'll look at that in a few minutes, very specific on some examples within the group. More broadly speaking, the housing sort of strategy that we've taken has sort of broad citywide effects of trying to sort of map where people live versus where they work and try to look at ways that we can densify areas that are maybe lacking in population density during the day. And so these are examples of, for walkable London, and trying to find areas which are maybe cut off or islands from walking to transit that may be opportunistic for housing, are also looking for areas that are, you know, direct proximity to the tube because they are more saleable in a sense. Oop. Back. So how do we densify in the city? There are a number of ways. We would all love to have a green build site and make something amazing on it, but often we are not left with that. So to be able to exploit what is available in the city, it often means that we are looking through or scrubbing through data or trying to search through the fabric to try to find opportunities that other people would not find. This may be small 10, 15% bits of lot. In this case, we're looking at ends of estate blocks and trying to identify how many there would be in a city and how much that portfolio would be worth if we were to develop it. That's just one opportunistic way of looking at the city. So if there are ways that, we can densify the city through a number of these opportunistic means, I'll switch this over again. Okay, I'm back. Then we will be better poised to deal with sort of the housing scenario that we're in, where we could use a lot more housing within the city because there's a demand. So a lot of non-standard shapes, sizes, and sites. These are ways to think about how we exploit what is available within the city fabric. Okay, so where we left off, I was just finishing talking about some citywide initiatives to sort of find sites to be opportunistic and to sort of look at the city in a way that we can incrementally increase a portfolio of housing options in the total portfolio of housing possibilities. So I'm going to keep moving forward here. So this is a relatively narrow lot in a high urban situation in New York. Very relatively low rise, but the trick with this one is how we get light and access into a space that is otherwise, you know, not set up for that eventuality. So one of the strategies that we start looking at is we look at the amenities first. And where are we going to put the amenities? And what will the amenities be? And if the amenity in this case is just a void space or the amenity is a terrace, then that already starts to give us nodes to start to link up space and to start to suggest how we might move the units around to allow for that to happen, which is a slightly different approach than sort of, you know, the efficiency approach of let's put them as close as possible. But the amenity itself provides a sort of light well in this sense down into the space. So as a theme, this sort of carries through with some additional modular construction thought in both the space planning for program and also the fit out. And as Vishu already mentioned earlier in his suggestion, in his architectural geometry presentation was, is this not going to play, is the use of sort of early intuitive non-engineering approaches to approximate equilibrium and to approximate self-stability, because it represents a state which would be less engineering obtuse. Here we're looking at sort of the load that would be transferred between any pad. Notice that the lowest one is the most loaded, while the top one is the least loaded. So this theme continues to densify. I'm actually going to show a few different levels of implementation of density to show how we are studying it in the city. That one was very dense, but only a few units. This one is more units, but they are much less dense. So if given sort of a broader site, how would you fit this out? So, I mean, if you were to do sort of an estate house again, it would be sort of a linear strip foundation. But if we were to take the approach that we want to have fewer foundation pads, or that we want it to be temporary, or that it's in an existing estate yard that used to be a parking lot in this case, then if you were to do it this way, you might need it temporary, at which point you could renovate the estate behind it, and then the occupants could potentially move back. Or it becomes another way to infill the site. So this was a proposal for Regent's Court along the canal in London for a G+3 build out, very loose in terms of density, but trying to make use of another sort of leftover space in the city that directly affronts the waterfront. And to try and build sort of a waterfront area in front of that. So it's not just about air, we also need to get light. So this theme starts to come through in sort of how we arrange space and arrange amenities. So in this particular algorithm, it's basically plotting recursively. Each iteration, it is absorbing where the light would hit it to generate where the pixels would be in space to arrive at a solution that has so many units that have enough light as sort of an erosive strategy on a given mass. And this is just a repeat from another vantage to give you sort of a look at this. But that allows you to start to think about space very porously, but at the same time, this is still a very dense development. If we were to do an efficiency calc on it, it would be very high. And fundamentally, the backbone of this is a double-loaded corridor, but it has a playfulness about the terraces and a playfulness about the removal of units to where it becomes sort of, it becomes less visible and blurs the boundary of what used to be sort of a double-loaded thing versus now what looks like a field of units that have micro-terraces. So this one is set out to be micro-terrace friendly, and all of the units sort of sit around this. We first start suggesting in this one also like a kit of parts that there's a balcony that could be shared or that has multiple states that it could be. It could be no balcony, balcony, two balcony, this kind of thing. So sort of look at this from the inside. Now this is maybe more towards, you know, young professionals or co-live or student housing. I mean, it is a tight sort of courtyard here, but to be able to offer additional residential and housing stock is what we're after. We're not trying to say all housing has to be this. Quite the opposite. What we're trying to say is that if there are opportunities to provide density, let's take that and do it. Let's get some more density where we can and sort of pick our battles. If we need to do a different product in a different location, we would do that. But what are the opportunities the city affords? So that gets me to the next thing, is thinking about how small can we go? If we start thinking about micro housing or pocket living, what in sort of the Stanley Kubrick sense for people in film out there, like if we just open up the door and it is a clean room and all of the furniture is modal, like what would this look like in sort of a very contemporary, almost futuristic way? If we were to hide or mask everything and start to think of the room as just a living area and everything else is just a detail. Behind the wall perhaps, or in this case above the ceiling. So using the vignette of a thick wall to hide or pocket all of the particulars. In this case, the thickest part has the wet amenities at the back with drier things successively happening at the front, and a sunken sort of area for lounging or inviting a friend or two over. Let me see if this will play. But to try to think about removing particular distractions in one's vantage as you get smaller and smaller of a space, trying to make it look less chaotic or to be more open becomes very important. What you don't want to do is have many, many things all over the wall when it becomes smaller, and then it feels very cramped or very cluttered. So the emphasis on the aperture or the emphasis on the windows in this case is highly intentional. And so thinking about micro pocket living and micro housing as modal, having things behind walls, in walls, in this case, sort of a platform for a low bed in the ceiling that drops down only when you need to sleep, otherwise it lives up in the ceiling, are ways to think about modal living. So the plan in this, as I said before, sort of a thick wall and trying to take advantage of that thick wall, both for structure, but also for all of the wet capacities within it. as we get much, much denser, we're starting to ask ourselves, how would a housing typology be different if it were the same count? So this was a project for an exposition in San Francisco, but the siting is in Mexico City, trying to compare two masses of the same basic square footage that would have 300 keys. So on the tall tower on the left, this would be 300 sort of for sales units, but on the lower ones on the right, these would be rentals. I think the text is reversed on this one. It's actually opposite, but the rental units would be the smaller ones. So why would that be the case? We're trying to have more active areas, less sort of seclusion, and so getting people closer to one another in a way where you can activate the social realm is very important. So in the lower area, we're keeping it mostly open, almost to a retail fault on this particular view. But in the upper views that are sort of shared areas where there's constant visual communication between corridors and ground level, where you can have active living from most vantages. And trying to continue to have a focus on what becomes an amenity, in this case, sort of a jogging deck with a spa area and pool with sort of a central core at the middle, which becomes sort of the umbrella for the topmost part of the tower. And thinking about accentuating these in the same way that Vishu was talking about the sort of tectonic or the architectural geometry, expressing where the activity is with warmth, in this case, the sort of under canopy of the wood. In the same way, we are doing this methodically from sort of aesthetic and tectonic and geometric aspects. We're also evaluating what's in front of us, or saying what are the benchmarks for it, or what feedback can be given. So there is also always some mechanism of analysis that goes along with this. And as Vishu said, with sort of the real-time solar tool that we're working on, there we also continue to garner analytics as we go. In addition to this, we're building these things parametrically. So this is just to say that these are very lightweight models, lightweight in the computation sense, in that they are built from, in this case on the left, probably a mere 10 faces equals a balcony, which is highly smooth and becomes then variable on a number of conditions. So one of the themes we are also going to talk about a bit is whether it can be something which is standardized or something which can be bespoke. And housing is driven by efficiency numbers. And this is something that we cannot take for granted, that we have to deal with it very directly. So the way that you can encode space to be standardized or universalized, and then to have percentages of bespoke or percentages of non-conventional delivery, begins to make it more communicable to others, either in fabrication or delivery, or other partners or collaborators you might need to discuss these things with. So moving on, this is so moving on to sort of thinking about how we do housing on hillsides. This has been a particular challenge that we've had a number of times since this particular competition, where we were looking at how we access units from the top, which is unusual in the sense of, if you traverse down a hillside, how you deal with access in multiple cores and multiple footings, but still retain sort of a promenade. But the idea, again, of activating a public way or an amenity thoroughfare, which is an active living space, is what makes this project sort of memorable. And not just that it's 30,000 square feet of student housing, but rather that you can access any given hall from the top. It's a continually connected rooftop terrace with views off onto the bay, and you can drop down into your particular cluster from any given sort of unit on the top. And this interconnected way has sort of overtones of the high line and continual vegetated occupation, which is intentional. It's about creating a continuous entryway. So we see here sort of thinking about how we activate sort of the public realm with multiple rooftops, multiple sort of mosaics of ways of thinking about rooftop terracing. Still very conceptual in these stages, but some of the core ideas are still underneath. This particular project exposed us to thinking about massing very quickly and very sketchy and on a hillside, trying to capture that data numerically, but for optioneering sort of thinking, like how quickly can we think of it if it's courtyards or if it's wings or if it's orthogonal or if it's rounded or if it goes with the contour. So systematically deploying mass on the site and then trying to get the numbers out of it became a challenge. So we're also responding to those internal problems as a team. So here directly after this project, we're looking at how are we going to test fit capturing large numbers of square meters or large numbers of units in real time so that I don't have to place them manually next time. So, you know, we sort of take on board, we have to do things manually sometimes. It's the best way to do it. To start, we do it analog and we'll get it wrong a few times, but then we'll learn how to make a better digital tool. Here you see the purple part has units which are pencil thin, but the rest of the tool sort of starts to go in the right direction, that it's not a design tool, but it's rather to get me to a point where I have a credible amount of area and a credible amount of units very quickly for any shape that I can think of. And so this is very helpful to move through options without necessarily having them correct, but if I need to get numbers very quickly, it's a relatively good way to approach the problem. Hillside, and in this case, we had a lot of constraints, so I was going to show you some sort of real-time construction optimization that we had to do on the delivery of this project, where with a continuously snaking spine that is interconnected, any move that you make on one of these junctions affects all of the other junctions. So if I move one left, you know, a meter or two, that actually pulls the angles all out of alignment, whatever. So we needed to develop a tool to be able to fix this, which meant communicating through sort of CAD means, encoding very sort of rudimentary blocks into what became a graph, and the graph has sort of links in a chain, and these links in a chain try to basically move little bitty snippets of space around the node. So you see on the right, there's a sort of pink area and a blue area. And if you were to move the pink area closer to the blue area, it would probably be a better node. So we try to tell the computer to do this. And when we tell the computer to do this, we can effectively get it to rationalize what is an otherwise not so regular geometry. And so we end up with very geometrically acute nodes with very regularized all the way to like degree 9 of tolerance 0 on the angles, which is needed for BIM. And also, the wings and base spacings are truthful to what they need to be for the construction grid. So in the end, what we're doing is taking what's on the left, which is sort of a strangely shaped triangle, and then making it the other triangle, and in the middle of all of that, making sure that all of the room spaces remain the same. So a bit of kinematics here and a bit of particle physics, but in effect, this is one of the optimizations that we had to do, which effectively spits out a construction grid set out in the end, which goes out for structural. So we're also thinking about other ways of mapping, not just solar and environmental, but also other performance ways of mapping. So whether in this case, the blue is thinking about overlooking if I can see in someone's room, or if it's how tall off of the ground. And these become other ways of thinking about how we might encode data onto the facade. So in this case, it ends up being a way that we think about tiling or coloring specific panels, but this is not that much different than when Vishu is talking about the Stratasys chair encoding particular color plates or perforations in the chair. We're trying to find ways that data can be represented visually so that you can respond to something about the environment around you as a performance factor. It's not performance in the sort of engineering sense of performance, but it is an articulation of how something can be expressed. We are now more engaged in trying to get more participants involved in the design process to try and make it an earlier design procedure to bring more and more people on board early and to engage, I'm going to get this to play, and to engage others in a participatory process where they can build either their community, their particular interior fit out, or how they would want to sort of reside within other clusters as operators. And in the same way, you may pick your flights, or in the same way you may order furniture from IKEA. These things we want to bring to you much earlier in the design process. So we're exploring ways of how we get that variability to different types of users, whether it's the end user who's occupying it, whether it's the operator like a Marriott who wants to just run 100 of these at a time, or whether it's an investor that wants to know that it's a sound judgment call. All of these things we're trying to look at how to discuss those very specific metrics with them all in sort of a round table. So a digital round table of actors, and how do we get all of their opinions to sort of come to the center, is how we will get much closer to having early real-time feedback in thinking about design problems. And regulatory is an excellent one. How can we encode that in early as well? But other things, and fabricators and engineers and the typical ones that we would interface with as well. If we can get digital participants of them much earlier in the design, then it means we can move faster through a design project. So Shajay mentioned we're doing this project in Honduras, and it's very much being done in this way of thinking about participatory housing and how you are able to engage and to choose your particular unit, your particular fit out, or your particular cluster, and how it resides on the hillside, to the extent that if you were an operator, you might choose the different site-wide amenities, or if you are going to buy your own unit, you would be able to pick and choose different options that are available to you on that unit. And so we're thinking about it in this way, that how can we describe this in a very saleable way that engages the user, but also gives them many options, because this makes it more saleable and more palatable to a broader audience. Digitally, what we are doing in this particular case is having a number of shape objects that have within them a number of nested shape objects, and those represent what become the envelope and then what becomes the space plan. So the space plan on the inside is sort of a collage of a number of pixels that are then being expressed. And based on the number of pixels that are expressed, we're saying that we might fit them out attuned to a particular persona. So maybe if you want to entertain people, you would have a larger living room. If you have a family, maybe you would have an extra bedroom or more storage. Or if you had, if you were just a young practitioner and all you cared about was having like an open floor plate and a lounge chair, like these types of things, we're trying to attune design options as styles to individual personas. This makes it actually easier to engage with different audiences because it's no longer a CAD procedure. We don't have to discuss whether they want the wall to be here or not, but rather we're discussing qualitatively what they would prefer their environment to feel like. So this is starting to look at sort of what the insides would be, very conceptual, but the idea that there are sort of, this has sort of a lounge pit, or that the bed and the storage is built into the wall, and that there's an overarching canopy that sort of does this. And I mentioned sort of flight seats, and this is one of the ways that we're thinking about how you can actually map or be able to see who is sitting around you, and if you want to sort of build a community around individuals. And we're thinking about this on the cluster side as well, like thematically, if you're more attuned to be like want to go to a gym or a cinema or these things, that individual clusters will have these amenities and sort of built around this as the identity for that particular set of units. Qualitatively, some of these environmental factors get fed back to us from the engineers. So in this case, looking at these 4 clusters that are on the hillside, and the left one and the right one having very different sort of wind and solar profiles. And this is something we can qualitatively express and people may want to choose. which one you would want to live in. So exposing transparently what some of those qualities are in a visual and illustrative way so that people are allowed the choice or the freedom to make that choice. If they don't want to, then that's their prerogative, but at least we are exposing data that would otherwise have been lost or not calculated, and it becomes monetizable, which is very important. If you can find a way to extract data that becomes relevant as a filter, people may want to pay a premium for that. And the client has been sort of very keen on thinking about ways to monetize externalities. Another interior sort of perspective. Yeah, Vishu?
We can leave you with a real world example of the configurator. Yeah, so this is the current state of our configurator where the users can interact and pick up their choices, pick up the unit they want, the house planning. So it's kind of capturing all of the things we were discussing, right from architectural geometry to computational housing and other performance metrics, which Henry was highlighting. All captured into a gameplay kind of thing, which will become more and more, will include other stakeholders into this framework in the next subsequent months.
Yep, so I can leave it at that. I mean, I think this is a good ending slide as well.